Hello, everyone. Hello, everyone. So let's just share the page course and share a screen. So, hi, everyone. Welcome to Fundamentals of Geomechanics. I am Mohammad Wahab. It's a great pleasure to have this course together this semester. So, the topic that we are going to have this semester will be Fundamentals of Geomechanics, which will be the introductory course to geotechnics at UNSW. But before we proceed, let's just have a poll together and also try to answer this. So, polling, who is with civil engineering background? Sure I am. Love to be. So please answer this to me before we can go and proceed with the course. So, as I said, the topic that we are going to have is Fundamentals of Geomechanics, Stephen 9525. This course is the basic course that you are going to have in our group, Geotechnics. Our group at UNSW is well known in unsaturated soil. The head of the group is Professor Nasser Khalili, who is a rated scientist worldwide in unsaturated soils. You must have heard his name. So it's a great opportunity for all of you to get involved in geotechs group at our groups, and this will be the opening door to all of you to start. Fundamentals of Geomechanics is actually an advanced soil mechanics. It's some sort of course refresher for those who are with civil engineering background, but for the rest who are possibly with the background of geology or other engineering disciplines, this will be a totally new topic. So keep in mind for the second group, this course will be full of challenge because it's essentially the most difficult topic for undergrad. So you should try your best to get the concepts as much as you can. Be active in the class, ask your questions, and also try to solve and practice as many questions as you can. There are a lot of topics involved. Do not be scared of this topic. We are not going that deep into every topic, but we are going to cover quite a good number of topics so that you become well prepared to do other topics at our school. The primary reference that we are going to use in this course is An Introduction to Geotechnical Engineering by Holtz and co-authors. So this is the primary textbook. It's available at the lab, so at the library and also bookstore of the uni. If you wish, you can actually purchase it for yourself. The other important and reputed references in geomechanics are Principles of Geotechnical Engineering by Dust. This is one of the most classic references in geotech. So if you have difficulty with this course, especially said if you have with different background, I strongly recommend you to actually go through that as well. It contains a lot of good examples, so it's good way to improve your skills. By the way, there are many more references: Lambert, Smith, and Craig. Craig is a little bit more advanced in case you wish to proceed with this. I strongly recommend you not to start with this reference. First, go to the other references. Once you are quite proficient with this, then go to Craig, because it's quite an advanced and challenging book. So let's talk about time schedules of our sessions. So we will have 10 weeks this semester. Week 6 is actually a semester break or non-teaching week. Every session we will have a series of lectures and also some workshops. In week 5 and week 10 we will have quizzes, as you see. Please note, these quizzes are extra marks, are bonus marks. Attending these courses, these quizzes is not compulsory for you, but it's quite challenging. It will benchmark for your skills and milestoning your progress with learnings and everything, and at the same time it will give me further feedback on how good you are doing. So please make sure you do the arrangements for both quizzes. And for the workshops, starting next week, the first 1.5 hour, we will have workshops where Noor will actually join the course to deliver these workshops. Noor is a PhD student, is a senior PhD student, quite an expert in soil mechanics. She has done these workshops for many years, so she's quite experienced and has done great with this course. So I strongly recommend you to actually attend both workshops and also the lectures. So how can you interact with me during the lectures? You just down here, you can find raise hand if you wish to actually share your experience, give me some comments, ask any questions. Please just raise your hand, and then you can share your video if you wish, and also your voice, and just ask your questions. And please keep in mind that always make sure you mute yourself, otherwise the voice will echo and the quality of my voice will be totally get worse for everyone. Okay, and I can see great that 47 are with civil engineering background and 7 are from different backgrounds. It's good to have more people who have had the experience of civil engineering, but the remaining do not need to be worried. You can be in contact with me more than the others. It's always the same. Students with different background get back to me quite frequently, and I will try my best to resolve the issues. So as you see, you can chat here. In case you wish, you can chat together or you can chat with me. Both are fine. Please note, all workshops, everything will be recorded. And as I told you before, on the left top here, you can find, it's currently recording, but once finished, you can find the recordings just left hand side, okay? So let's get back to the lecture. So as I explained, we are going to have 10 weeks, and I briefly explained how we are going to deliver the course. So some general comments. Please try to have 100% focus on the lectures by keeping your mobile silent or not texting, no use of phones. Have a good night of sleep. I really don't want you snoring by the end of my class. Be on time. I prefer not to waste too much time at the beginning of the class to make sure all of you have joined. It's just being respectful to everyone, so I really appreciate that. Try to get every concept in the class. Please note, of course, it's online, but I'm here to help. Any questions that you have, you can ask me. You can raise any difficulty that you have, and try to be interactive. Don't be shy. So just note your handout could be a little bit different from the presentations, but not that much. You do not need to be worried about anything. And again, try to be active participants in the workshops, particularly because the lectures I issue the concepts, but during the workshops you are going to be challenged with different examples. So do not miss them. Otherwise, you will regret that. I just heard someone maybe raise hand. When is the workshops? No. The workshops, as I explained, the workshops will be the same time as the courses. So every week we will start at 5 and will be finished by 9. The starting will be the workshops. It will be from 5 to 6:30, and at 6:30 I will join the class to actually deliver the lectures, okay? And as I said, everything will be recorded. So let's just proceed to the next one. The content that we are going to study in this course. So we just start with introductions to soil mechanics. We start with phase relationships, classification of soils, and compaction. These are the elementary topics that we are going to talk about. But we will give you some insight about how soils are classified and one very basic application, which is compaction. Next, we go with stresses in soils, where we will introduce more circle and also discuss effective stress concept. Our next topic will be water flow in soils, where we start with the simplified one-dimensional seepage, followed by more advanced two-dimensional seepage. Our next topic will be an important application, settlement, where we first introduce long-term settlement and then go to rate of settlement. Soil strength is one of the most challenging topics that we are going to have. So soil strength, we will start with drained and undrained conditions, and we will discuss frictional and cohesive soils. We will target these sort of strengths that soils show. And the last topic that we are going to have will be introduction to soil stability. For those who are more interested in geotechnics, in applied geomechanics, if you take the course, you will have soil investigation, where site investigation and lab tests are introduced and discussed. Later on, foundation design for both shallow and pile foundations are presented. Retaining walls is also another important topic that is discussed. Slope stability, but in a way more advanced way, is presented. And one of the most challenging group of soils, which is expansive soils, will be discussed in applied geomechanics. So let's talk about the assessments that you are going to have in this course. So you are going to have a series of assignments with 3 submission dates. You can see the weights of each submission. The first submission will have 10%, the second one will have 15%, and the third one will have another 15%. So just note that you can find the submission dates in course profile. And about the consultation times, it will be Fridays from 10 to 1. And my office and also my box are both located on level 5. It seems that you will have limited access to the campus during this. If you wish to have face-to-face consultations, it's not approved yet, but maybe you can come same time. Okay? And for your submissions, please note this semester we prefer online submissions. Please also make a copy of your assignments and keep it in case anything happens. So I think there was another comment. Okay, nothing. So as I said, online submission is preferred. So I will actually create a link for you on Moodle, and then you can just submit your assignments online. It's just the easy way. So just more explanations about how you should submit your assignments. This is a sample assignment. In each assignment set, you will have the final answers, and with these final answers, you should include your final solution. So you just write out your answers here. In case your answer is exactly the same as provided or with reasonable accuracy, there could be, for example, the last decimal number could be slightly different, that's fine. If you reach at the correct answer, just place a tick here. In case your answer is totally wrong, you should place a cross. And in case your answer is not exactly the same, for example, here you have another figure, let's say 119. It's relatively close. You don't know what have you missed, so you just place a tick and a dot. Okay, so you should attach this form to your detailed solutions. So keep in mind, I want you to submit both your detailed solutions and also this checklist. Okay, And based on these, you will receive your mark. Your trustworthy is quite important with these self-assessment. I expect you to have all truly set here. Otherwise, you will lose a lot of marks, okay? Just one final note about the assignments. I have already posted the assignments on Moodle. You can find them. And based on your ZID, you should pick a set of assignments. And you can also find details on this submission dates and everything else on the course profile. So about final exam, it will have 60% of your assessment. It will be open book, and in order to pass, it's the policy of the university that you should get at least 40% in the final exam and 50% in total, okay? There are some policies about sitting in exams that I have copied it for you. Most probably we are going to have online exams unless things change. But during these times we had all the exams online, so expect the same. Now let's talk about the objectives of this topic. In this course, we are going to deal with soils. Soils are small particles of minerals or matter, which are simply broken up pieces of rock, could be resulted due to weathering or other geologic processes. Soil is an engineering material whose properties and behavior are very important to us, and the reason is that we are going to build upon it. Otherwise, it was not that significant to us. It's we have wide range of civil engineering applications and projects where we have to build upon or within the soil, so it is extremely important to be able to deal with soils. But the thing is, soil is quite a complex engineering materials. It is non-linear, non-conservative, anisotropic, and heterogeneous. And the objective here is to actually find an order in the behavior of the soils to be able to tackle with them in our engineering applications. So, as I raised before, civil engineering projects, all civil engineering projects deal with Earth surface. We either load the soil or rock. As I said, we might be dealing with some excavations and fields. It could be even deep in the ground, like tunnels and these sort of things. So here you can see some classifications of simple civil engineering projects. For example, whenever you are going to construct some houses, you will have to actually transfer the load of the weight of the materials to the ground. So you have to actually build some foundations which are for short and light buildings, just some isolated foundations. Whenever you have taller buildings, you will have to have a more solid foundation, which could be a mat foundation. Sometimes the soil is quite weak that you absolutely cannot rely on the soil. So in these cases, you will have to actually drive some piles into the soil. Sometimes because of the basements, it's the most common thing now, you will have to excavate the soil for construction of the roads, it's the most generic application that you have to construct fields, and for tunnels, one of the major applications for excavations. So for the houses or this sort of buildings, your concern is to determine what are the dimensions of the foundation based on the strengths that you receive from your soil. You see, this is the soil this is the weight, and this is how pressure is distributed towards the soil. Whenever dealing with piles, your challenge is to determine what length is required for these piles so that the load is quite safe transited to the earth. There are different types of piles, wooden piles. They could be even in water, like these ones, and they could be driven this way in dry lands. There could be even concrete. There are also solid steel profiles used as piles. They are also as effective. Whenever dealing with excavations like this one, so we will have some vertical loads and vertical distribution of stresses in soil. But in addition to that, we will have another challenge, which is actually the lateral pressure. So the more complex we get in our projects, new challenges will rise. With these sort of fields, so sometimes it's actually not sometimes, always. The challenge is what is the safe slope that we can construct. So if you just assume some curves, they could end up in failures. So it is important to be able to estimate what is the slope stability, what is the range that we can rely on our soil unsupported. Otherwise, we will have some mess like this one. For tunnels, now we are deep in the ground, so the lateral earth pressure will be quite huge, and we should design a tunnel, the walls of the tunnel, such that it can stand the loads. So let's also talk about some other important topics here, important applications here. So retaining walls, as I explained, we can construct the soil slopes at specific degrees, otherwise we cannot rely on its stability. In these cases, we have to construct some retaining walls so that it will actually withstand the weight of the soil here. And in cases you have some construction, it will definitely change the distribution of the stresses. So we should be able to estimate that these changes, which are quite significant and important. Retaining walls could be wooden ones, could be built with rock, stones, and in more major applications, when we are dealing with relatively tall retaining walls, it will be precast concrete, or even some really major ones like this, where we have quite a tall concrete retaining walls. Retaining walls are quite important and challenging. I don't know if you have heard of the current challenge in Queensland. So it's quite big challenge to have these sorted out, especially whenever you are dealing with sea as well. Soil structure interactions. So we always are dealing with soil structure interactions, but most of the times whenever we use this term we are dealing with relatively tall buildings, and also one of the major cases is earthquake. So let's start with one of the important cases and quite complex cases, which is dams. So I think most of you have seen big concrete dams like this. So in these cases, we are dealing with huge amount of water pressure, which is applied on only one hand side of the dam. This will be transit towards the corners of the dam, to the walls of the of everywhere the dam is relied upon, and it is quite a huge load. It will actually generate huge displacements, more than you expect. Another important type of dams is earth-filled dams. As you see, sometimes instead of using concrete for construction of the dam, it's more economical, and there are other reasons that we construct earth-filled dams. We use different soils, and at the middle you can see it's totally different one. This is called the core of the dam, which is actually a relatively low permeability clay. So we have water on one hand side, and the difference here is that water is seeping throughout the dam body. It will be one of the important topics that we are going to discuss here into the seepage. Offshore foundations. So in petroleum engineering, it's one of the most important challenges to be able to construct offshore foundations like this, and it is definitely one of the most challenging ones in civil engineering. So soil behavior is important to know, because we need to know the engineering properties of soil, and we need to be able to estimate the capacity of the soil in bearing loads. The displacement of the soils are important to us in many cases. Water flow and also stability are the major things that we need to know in soil behavior. Sadly, inappropriate interpretation of these behavior of soils has resulted in catastrophe. Let's just show you a few cases. So, blunders, one of very famous ones, has been in Niigata earthquake in 1964. As you see, after earthquake, a lot of buildings here have overturned in this way. Some tilted small, but some significantly overturned. So as you see, the structure of these buildings is not affected that much, which is representative of relatively reasonable structural design, but sadly very bad knowledge of soil structure interaction. So you can see here a few cases of soil subsidences. As you see, the buildings are not that high, only 1 or 2 stories, but as a result of soil subsidence, everything is just collapsed. This is another case of overturning. So again, you can see the building is quite in a good shape. You can see just a few small cracks here, here, and here. But the building looks quite fine, but unfortunately, the, the foundation has been just a matte foundation, which seemingly has not been enough to resist overturning. And keep in mind, there is absolutely no way to save these structures. Everything is lost. They could be even very good buildings tilted like this. And even small tiltings could be problematic. As you see, whenever two tall buildings are relatively close, as soon as they touch, the problems will start to actually grow and grow, and eventually you will have big problems. The other case of our blinders is a very famous case of San Fernando Dam in California. The case was in 1971, where actually one side of the dam was actually eventually damaged and everything was just ruined. This is another case of overturning of a structure. Again, as you see, the building is more or less in good shape, but unfortunately, it has fully overturned. I really don't think any one of you wish to be in any building like this. Uh, it will be real serious thing, and as I said before, everything is lost. There is absolutely no way to recover such things like this, even though the building could look in a good shape itself. Another important case of our blunders, failure of Teton Dam in 1976. It is famous because it's well photographed. So as you see, everything looks quite neat and clean. Eventually, just at this zone, eventually a hole has appeared and water started to rush from one hand side. And as soon as you have this hole, everything will be lost. This is the final shape. So even one single mistake could be big trouble. This is another case. This could be a little bit lucky because this is a beam in a bridge. So even though the support is actually tilted, the structure is not fully collapsed. So this could be recovered, but it will cost too much. And sometimes these blunders could become quite famous, like Piazza Tower, which is actually a monument. I don't know if you have heard the story of what has gone with Piazza Tower. So it was constructed in more than 500 years ago, as far as I remember. Eventually, in time, this tower started to tilt, and it kept on tilting and never stopped. So they had to evacuate the building totally to see how to work it out. It took a lot of money, long time to test different ways so that they could resolve this issue. Unless this was a history, because it was a historical monument, otherwise they would definitely forget about it because it cost, the expenses are too much. You cannot believe it. So the issue with this building was that just beneath this building there was a sensitive layer of clay in this way. So as you see, the thickness on left-hand side has been relatively short, but on the right-hand side, we have had great lengths of sensitive soil. So whenever you deal with sensitive soil, it will actually show a huge amount of settlement. That's why the right-hand side here has started to move down, and further down, so that it will get into the equilibrium. But the structure may not sustain that huge amount of displacement. So keep in mind, even one single borehole and very basic knowledge of soil mechanics could avoid all these headaches and all these expenses. So another case, let's assume this is just a plain land, and you are going to construct a building on it. So if you just overlook geotechnical engineering, let's see what could happen to you. This. So a brand new building is just constructed on a soil, and immediately soil subsides and everything is just lost. Again, keep in mind basic knowledge of geotech, and also one borehole could avoid everything here. Be even worse, like this, quite big, has actually ruined a neighborhood. So let's talk about historical milestones in geotechnics. One of the earliest scientists in geotechnics was Charles Coulomb. Charles Coulomb actually was the first who could develop some criteria for soil shear strength and also soil failure. It's still one of the robust theories, and it's used widely, and we will introduce this in our course. Later on, in mid-80s, Darcy developed an expression for soil permeability. Now you know many cases that water seepage in soils be of significant importance to us, and we are still using the same Darcy law for soil permeability and water seepage in soils. So quite significant achievement. Another big name in soil mechanics is Ranke, who has developed some solutions for stresses in soils. Again, quite applicable now. But the biggest step forward in soil mechanics has been in 20th century by Carl Terzaghi, who is known as father of soil mechanics. Terzaghi actually has been one of the most brilliant scientists in history. He has won a normal medal of ASCE 4 times, which is quite big achievement, one of the biggest achievements in civil engineering. ASCE is American Society of Civil Engineers, so this medal is the most prestigious one of that. He has 9 honorary doctorates from 8 countries, and he has officially started the modern soil mechanics, and his single most important contribution to soil mechanics has been the solution of consolidation. This is one of the most challenging problems that we are going to actually discuss it here, which is used for evaluation of settlements of soils. By the way, he has done way more, including lateral earth pressure, estimation of bearing capacity and stability. So he has been, that's why he has been the father of geotechnics. His book is published in 1925, and from that date, soil mechanics has started to become a single discipline by itself. So this was the last slide for now. Let me stop sharing. And get back to you. So, any questions from you? Let me also check the chats. I can see some are asking about the assignments. About the assignments, I will, as I explained, I will add a link in Moodle so that you can actually join it. You can upload your assignments on that. I have already uploaded the assignment sets, and you can read my message on which assignment is associated with you. And about differences in your answers with the given answers, keep in mind you should try your best to reach all of the answers. Okay, it's the most important self-practice that you are doing in this course, so I really expect you to try to reach at the correct answers. So some of the students are asking about what is the checklist. I think it's best to share one of the checklists with you so that I can explain a little bit more. So let's see assignment A. It will be a series of assignment sets, number 1 to number 10. In total, it is very close to 40 questions in 10 different sets. As I said, the final answers are provided. Just write your answer here, and in addition to detailed solution. Okay, so you should attach detailed solution as well. And if it is 100% correct, just place a tick. If slightly different, just place a tick and dot, and otherwise place a cross. should we need to upload the process of the calculations? Yes, you should. So as I said, I expect you to actually have all the solution details, how you have done the solution. It is important to both you and myself. Firstly, if your answer is correct, I can check if you have really done it right. And secondly, if your answer is wrong, I can quickly check what has been the issue, and later on, if possible, I can give you some feedbacks about that. Okay, so this was the first lecture. For now, I just last questions for now. So should we upload the scan copy of handwritten file or type in the Word or any? It's totally up to you. If you wish, you can write out your solution on your surface and just have it as a file or handwritten. Everything. It doesn't make that much of difference to me. For now, let's have a break of 10 minutes, and we will start the next lecture at 6:10. Okay, please get back on time. Okay, guys, let's just continue our lectures. So the first lecture that we are going to talk about is on phase relationships. So soils consist of solid particles, and also they contain a lot of voids. These voids are quite important to soils because these voids could actually be filled with air or water. So sometimes it could be completely filled with water like this, which we just call it fully saturated. Or like this case, it could be partially saturated with water. So voids affect the engineering properties of soils, and that's why we need to actually be able to classify them with a reasonable engineering process. To do so, assume a REV, representative elementary volume of soil, like this. For this, we can develop an equivalent phase diagram like this one, where we have all the soil grains all together, which is actually forming some portion of the total volume of the soil of the REV. Some portion is fully filled with water, and the remaining is filled with air. So we are dealing with three different phases in soil: air, water, and soil grains. So let's talk about our notations. The important factors that we are dealing with in soils are the volume, mass, and weight of the components of the soils, where we show it by letters V, M, and W. The indexes that we use are A for air, S for solid, W for water, and we have two more indices, which T stands for total and V stands for voids. Voids by voids, we definitely translate it to volume of air and water, this portion. So on the left-hand side of phase diagram, we represent volumetric contribution. We call it volume side, and on the right-hand side, we just call it mass or weight side. So we can simply show each volumetric contribution in this way. For example, volume of soil grains as Vs, volume of water Vw, and volume of air Va, V total, and also Vv. On the right-hand side, we represent both mass or weight contributions. So we will have some weight for soil grains and some weight for water, but we have no weight for air because the weight or mass of air is relatively negligible in any soil. So total weight will be the summation of weight of soil and water, or alternatively we can say all these things via mass. And as you might know, weight and mass are related as W is equal to m times g, where g is gravitational acceleration of S, which is 9.8 meter per square second. So our objective here is to be able to compute the mass or weight or volume of each component that you see in this phase diagram. Some simple and obvious relations are the fact that volume total is summation of volume of soil and volume of voids, or the summation of volume of soil, volume of water, and volume of air. And alternatively, for mass and weight, we can develop mass and weight total versus soil and water. An important point to note is about the units that we are going to use. So in this course, we use SI units and also CGS units. In SI units, the primary units that we use are meter, kilogram, and seconds. In CGS units, C stands for centimeter, G stands for gram, and S stands for seconds. And you must be familiar with the units for these things that we have defined: for length meter, for volume cubic meter, for mass kilogram, and so on. For density and stress, we have definition of Newton per square meter, where Newton actually Newton is a multiply of kilogram and G, and density is unit. Is the mass of unit volume, and unit weight is the weight of unit volume. Just some units in the CGS system. You are more or less familiar with this. I just skip it. Now let's talk about volumetric relationships. Always keep in mind, whenever dealing with soils, the total amount of volume of the components, or even the masses, in nearly all cases are not of that important to the mechanical behavior or response of the soil. That's why we have to develop some relationships between the relative ratio of these components. One of the most important volumetric relationships is the void ratio. Void ratio is defined as the ratio of volume of voids with respect to volume of soil grains, and is shown by E. The next important parameter is porosity, which is represented by N, defined as volume of voids over total volume. So for porosity, we expect that volume of voids does not exceed the total volume, so it is always less than 1. And another important definition is degree of saturation, SR. SR, degree of saturation, is defined as volume of water, so this part, over volume of voids. Again, for this ratio, volume of water may not exceed volume of voids, so again, degree of saturation is always less than 1. Indeed, the range is from 0 to 100%. When it's 0, we have absolutely no water, so it's dry condition. And when it is 100%, the soil is fully saturated with water, and it's called saturated. Anywhere between is just called partially saturated or unsaturated soils. As I said in the introduction, our group, in particular Professor Nasser Khalili, the head, is extremely reputed for the study of unsaturated soils. Some typical values for your own reference. Void ratios for sands are mostly in range of 0.4 to 1. For clays are in range of 0.3 to 1.5. For porosity, as I said, it's always less than 1, and you can see the ranges. And for the degree of saturation, again, you can see the range. Now, Let's try to correlate these important volumetric relationships together, these parameters together. So void ratio can rewrite it, and it is the ratio of volume of voids over volume of soil grains, which can be written as volume, instead of volume of soil, it can be written as total volume minus volume of voids. So the total volume minus volume of voids will be volume of soil. By using the relation of porosity, we can rewrite volume of voids as n times volume of voids, total volume. So we reach at n times v over v minus n times v. By removing, by dropping out v here, we will reach at n over 1 minus n. So there is a relation between the void ratio and porosity is equal to n over 1 minus n. We can do similar manipulations by using the void ratio, by using the degree of saturation to reach at similar relations. If you refer to textbooks, you can find an abundant number of relations, and just keep in mind these relations are good and useful, but if you are good in memorizing them. I personally am not, and I always recommend you to be able to drive all these expressions and always rely to the primary relations. So here the definition of E, N, and SR are the primary relations. You should keep these three in mind, and anything else you can simply drive. Weight relationships. In this course, there is one single weight relationship that is of enormous importance, which is water content that we introduce. So water content W is equal to WW over WS. So the ratio of weight of water over weight of solid or soil grains will be water content. This is the most important weight relationship in soils. So in addition to the three volume relation, this weight relationship is the fourth important relation that you should keep in mind. So we noted that water content is usually expressed as a percentage. It is typically less than 100%. I mean, the weight of water is typically does not exceed the weight of soil grains. But we have some important cases that we can have water content of 500%. These are extremely challenging soils that we could deal with, and where we have 5 times weight of water with respect to soil grains. So it could be quite challenging. So it is due to some marine soils and also some organic soils mainly. A simple rule. So let's do some further manipulations with our primary relations that we have here. Whenever you do not have any volume reported in your problem, a very helpful attitude for solution of your problem is simply setting the volume of soil grains as 1. So just take a look at here. We have volume of soil If we just set it as 1, let's see what will happen. Let's start with the void ratio. If we set volume of soil as 1, then the void ratio will be the same as volume of voids. So we can write it here. We can also elaborate the porosity. So porosity was the volume of voids, which is E over total volume, which is the summation of 1 and E. And finally, for degree of saturation, we can write it as volume of water over volume of voids, which is E. In this way, we can rewrite volume of water as SR times E. And the remaining will be the volume of A. So, whenever dealing with soils that we do not have any volume or masses reported, just bear in mind a very simple strategy is just the way that we explained, setting volume of solid grains to 1, and then we will have everything defined. In this way, you will benefit a real simplified solution. I will discuss it in the examples later on. Now let's go to another important definition, the definition of density. I expect most of you know it. Density is defined as a mass over volume ratio. You must know that density of water is 1 ton per cubic meter. We can do similarly for unit weight. So we define unit weight by dividing weight over volume, which can simply be shown as rho times G. And you know G is 9.8 kilonewton per cubic meter. And for soil, we can write it gamma S as volume, as weight of soil over volume of soil. Let's go to the next slide, where we talk about a specific gravity. A specific gravity is another important definition. A specific gravity is shown by GS, is defined as density of soil grains over density of water, or simply rho S over rho W. It can be written alternatively as unit weight of soil grains over unit weight of water, as gamma S over gamma W. The range of GS in the majority of soils is in range of 2.6 to 2.8. The average value for GS is 2.65. Keep in mind, in our course, whenever GS is not provided to you, it is very important that you use this value, 2.65. Okay? So keep in mind, this is quite an important point. Whenever GS is not provided, just assume it is 2.65. It is the most common value of GS. So let's go to the next slide here. Another important relationship. So if you continue the simplified solution of setting volume of soil grains as 1 and having the volume of voids as E and so forth, we can have the weight contributions on the other side. For example, volume of soil grains, we know that it is defined as gamma S times Vs. By setting Vs as equal to 1, then Ws will be equal to gamma S. And for gamma S, we know we can simply write as Gs times gamma W, and just set Gs as 2.65. Okay, 2.65, and in this way you easily have WS. For WA, we know that weight of air is negligible, and the only remaining one will be weight of water, which we can again simply correlate it by using its volume, where we reach at W times GS times gamma W. It can alternatively be written as gamma W E times S by using the volume from the other side. So, by setting the volume of water at both sides the same, weight of water the same by using different expressions that I explained, we will reach at this relation. Void ratio E times SR degree of saturation is equal to W water content times GS. This is a very popular relation, and sometimes for simplicity it's this way. George Washington is a soil engineer. In this way you can simply memorize it. It is quite a helpful relation. So in addition to the primary relations that I just expressed, I strongly recommend you to keep this relation in mind, and it doesn't need anything to memorize it. George Washington, soil engineer. Just note, in case that we are dealing with saturated soils, SR will be equal to 1, then we will have the void ratio as W times GS, which helps you a lot in the solutions. So another definition, total density, total unit weight. So total unit weight can be obtained by dividing total weight by total volume, which can be written in this simplified form. So gamma total will be equal to GS times gamma W times 1 plus W over 1 plus E. If you are good with memorizing relations, it is one of the relations which is good to know. Typical values for gamma total is from 15 to 22. So in addition to the total unit weight, you can develop similar expressions for saturated unit weight, which will be this one. For dry unit weight, SR degree of saturation or W moisture content both are 0, then you can reach at this relation, GS times gamma W over 1 plus E. And again, bear in mind that in soils, degree of saturation is in range of 0 to 1, for which at degree of saturation of 1, we reach at gamma D, which is the smallest possible value, while at as degree of saturation equal to 1, fully saturated, we will reach at gamma saturated. And another important definition, submerged or buoyant weight of unit weight is shown by gamma submerged or gamma dash, which is representative of the weight of soil when it is submerged in water. You know, anything submerged in water will actually become lighter and the same as the unit weight of water. So gamma submerged will be equal to gamma stat, which was this one, minus gamma water, which can be written this way. It will be an important parameter for us, but not now, later on, where we talk about stresses in soils. some typical values, as I said before, for total weight, the range is from 15 to 22. The top range is for saturated condition. The bottom range is for dry condition. And the submerged is actually obtained by subtracting gamma W from fully saturated case. So what is the solution strategy whenever we are dealing with phase relationships problems? These are the steps that you need to take. Firstly, list all the informations that you are given. I strongly recommend you to draw the phase diagram and try to fill in the unknowns and knowns, everything. Big formulas could be actually sometimes problematic, sometimes you may do some mistakes with the units. So especially whenever you want to just start learning, draw this phase diagram. In case no mass is reported, just follow the simplified procedure as I just suggested. By setting Vs equal to 1, then you will have every parameter versus E, and you can proceed quite easily. So try to fill in the parameters of the diagram on one hand side and keep on going until you get stuck or you cannot completely, unless you can completely solve it. The best strategy is to switch from one side to the other side, from volumetric side to the weight side, and in this way you will be able to obtain all the variables of the problem. Always make good use of GS, which I told you. Always use 2.65. It's the best engineering the estimate that engineers use in practice. A very important point in your problem solving is the fact that many of you do not use consistent units. Try to stick to one system of units. For example, if you are planning to going with SI units, then do it for every part of your example or problem. Otherwise, if you wish to go with CGS, do not switch too much or you may mess up the solution. And a tip for your solution is that always check the reasonableness of your answer. For example, if you are going to calculate void ratio, you know the ranges, I have just provided it to you, or specific unit weights, anything that you need, just try to check if it is in the range of in the typical range. Okay, it could be a slightly above or slightly under, that's fine, but it cannot be out of range. For example, for porosity, it cannot be 3. We do not have any soil with porosity of 3. Okay, just keep in mind that in these cases will show you there are some inconsistencies, especially in units. Let's do an example together. A saturated clay has a moisture content of 41.1%. What is the saturated unit weight? Assume gamma W is 9.8 and GS is 2.65. I will never provide these two values either in your example or in the final exam. Okay, you must know these these typical values. Okay. Here we just use the relation, the closed form relation that we just showed for gamma sat, which is GS plus E over 1 plus E times gamma W. So the second relation is E is equal to WGS. This relation is the same as George Washington is soil engineer with SR equal to 1. Okay? So WS is given as 41.1%. By using GS, we will obtain the void ratio as 1.09. By inserting this value in gamma sat relation, we will obtain GS 2.65 plus E 1.09 and gamma W 9.8 and so forth. Here we will obtain 17.54 kilonewton per cubic meter. So the solution is quite simple whenever you are using the closed form solutions. But this is not always comfortable to memorize all these solutions. So let's do another example where we have a little bit more complexities and trying to use the phase diagram. In this example, a cylindrical soil sample of length 100 millimeter and diameter of 50 millimeter, which has a mass of 326.03 grams, is assumed. After drying, its volume is 266.09 grams. What is the degree of saturation, SR? So let's just start with evaluation of the sample. We've got a cylindrical soil sample. The total volume of it will be pi times h d squared over 4, which will be 196.35 cubic centimeters. The total mass is given to be 306. Now we can easily obtain its total density by dividing the total mass over a total volume, which means 326 over 196, which will be 1.666 gram per cubic centimeter. Now let's draw the phase relation diagram and try to complete the components. So as you see, the total volume we just calculated was 196.35. The mass of soil grains, in order to obtain the mass of soil grains, let's refer to the question here. It said that after drying, its mass is 266.09. So the difference between these two is actually when we've got the soil, a mass of soil, and when we oven dry it, the water will just evaporate, and the remaining is just volume of soil, is the mass or weight of soil. So this 266.09 just goes to the mass of soil grains. And the difference between the total and mass of soil grains, which is simply 59.94, goes to the mass of water. Okay? Now we can switch to the left-hand side by using specific gravities in order to calculate the volumetric values. For example, for mass of soil, this is mass of water, which is 59.94. this mass of water will be the same as mass of water. In order to calculate volume of soil grains, we need to divide mass of soil grains by density of soil grains, which can be written as ms over gs times rho w. So we have 266.09, which must be divided by gs, which we set it at 2.65, which gives 100.41. Okay, so the volume of soil grains is 100.41. The volume of water is the same as the mass, 59.94, and the remaining will go to air, which is 36. Now we can easily calculate volume of voids, which is the summation of 36 and 59.94, which reads 95.94. We were asked to calculate degree of saturation. So degree of saturation is defined as volume of water over volume of voids. Volume of water in this figure is 59.94. Volume of voids, as we calculated, is the summation of these two, which is 95.94, which reads 0.625, or in percentage form, 62.5%. So this example simply showed you how you can use the phase relationship diagram. I always prefer to go rapidly through the examples, through the earlier that we have, and after that you can ask your questions. So in this example, we've given a cylindrical soil sample. The dimensions was given. By using these dimensions, we calculated the total volume of this soil sample. We had the initial mass of our soil sample and also the dried one. By using the difference between the mass of dried soil and the initial mass of soil, we could simply calculate the mass of water, while the mass of soil grains was the same as oven-dried mass. So we eventually completed the mass or weight side. For volumetric side, we tried to use GS in order to switch from MS to VS. We simply divided MS by GS to reach at 100.41 to calculate VS, and we did similarly for water, and could finally complete volumetric side and use that to obtain the degree of saturation. So there are a few more comments on this example. As you just saw here, we used CGS system. The reason that we use CGS system is the fact that we had relatively small values. It's always your decision to pick the system of units, but it's not the best choice to stick to only one of the options. If you had decided to use SI units, then you had the volumes at least with 7 decimal digit accuracy to reach at cubic centimeter, and you had more or less similar issues to reach at accuracy in order of grams. You needed to add 3 decimal digits and so forth for weight, and other things. So you need to be competent with both system of units that we just explained. Always, whenever you are dealing with small masses, small volumes, try to stick to CGS because it reads the easiest. Otherwise, whenever you are dealing with big masses uh, and big examples, and in these sort of applications, try to use SI units, okay? There are a few more examples that I leave it to your workshop, and Noor will solve them for you in the next workshop. For now, if you have got any questions, please feel free to ask me. Otherwise, we can have another break. Any questions for now? Okay, seems no question. So, no question so far. That's great. Thanks all. So let's have another break, and we can start at 7:05. Okay, 5 minutes past 7. Please again be on time. Thank you so much. Hi everyone. So let's start the next part, which is soil classification. Let me check if you have the voice and everything. That's great. So let's start what is the significance of soil classification? Why do we need to classify soils? What are the objectives? So classification of soils in a systematic way is extremely important in terms of engineering, in a way that all the engineers must have uh, the same language to communicate. For example, if let's assume we have different countries, in each country we have different languages. So unless all of people have the same languages, they cannot communicate. It's the same in engineering. So we should develop some classifications which are acceptable worldwide and useful worldwide, which enables us to communicate between different engineering groups, especially in big projects, which are international projects. So we should be able to apply appropriate names to each type of soil on the basis of its classification. Points to note are actually each group of soil should have similar geotechnical characteristics. It is of extremely important uh, uh, to note. Otherwise, if you have classifications of soils that ends up in different classes, which even do not have the same behavior, it's not helpful at all. And as I said, it should be internationally acceptable. And the other important thing is that it must be simple, cheap, and does not need high precision apparatus. Otherwise, it will be absolutely impractical. Just keep in mind, always engineering. Am I mute? Okay. Okay. Please, if any student is not mute, please mute. Okay. So, if any engineering approach is not simplified, it doesn't matter how accurate it is. It will receive no welcome from the engineering society. Okay, so always keep in mind to develop simple solutions. Complicated solutions are not welcome. Different classification systems. Three top reputed ones are Unified Soil Classification System, USCS, American Association for State Highway and Transportation Officials, AASHTO, and the other one by Massachusetts Institute of Technology, MIT. Here you can see some representative of how these soil classifications work. So the top bar is for USCS, the middle one AASHTO, the bottom MIT. And as you see, always very big soil grains or rock are referred as boulders, eventually cobbles, and then the important upper limit for soils. These are rocks. The important upper limit for soil, which is gravel, in USCS and AASHTO start at 75 millimeters. While in MIT, the upper limit for gravel is 60 millimeters. Eventually, if you move to finer materials at 4.75 millimeters in USCS, 2 millimeters in AASHTO, and 2 millimeters in MIT, you will reach at sand grains. And if you continue to moving towards finer and finer materials at 0.075 millimeters, you will start to have all the fine materials, which are silt and clays. In AASHTO, as you see, the upper bound for fine grains of clay and silt is again the same as USDS, but the distinction between silt and clay is still based on the size. It's the same in MIT classification as well. And just keep in mind, and just remind the most important thing that I said, engineering solutions must be simple. Whenever we deal with extremely fine materials, this range is extremely hard to work with. That's why most geotechnical engineers prefer USCS, but that's not the only reason. There are other reasons that we need to discuss. So USCS, as we explained, for coarse grains are based on the sizes. By coarse, we mean those which are visible to naked eyes, like sands and gravel. And with fine-grained soils, we mean silts and clays and organic soils, which are extremely fine and are not recognizable. So, in order to find the grain size, we always do the sieving. As you see, we put a group of sieves and just in a finding order, and in this way we work out how is the distribution of the sizes. The major sieves that we use is 75 millimeters, which was upper bound for gravel. Sieve number 4, which is the boundary between gravel and sand, and sieve number 200, which was the upper bound for fines. Okay? But the point that I raised about USCS, so distinction between silt and clay, as you just saw in this bar, fine grains actually are not distinct via their sizes. Instead, the behavior of these fine grains in presence of water is the factor which distinguish the fine grains, the silt from clay. Let's assume we've got a fine grain soil which is plastic, cohesive. By plasticity and cohesiveness, we mean this. By plasticity, the soil's ability to be molded. By cohesiveness, the soil's ability to stick together. Okay? If we have a soil which is plastic, cohesive, which has poor drainage, compressible, platy shape, and hardens when dry, what do you think? Do you think it is a clay or silt? we expect it to be clay. On the other hand, if a soil is non-plastic, cohesionless, fairly good drainage, incompressible, and bulky shape, then it is silt. The point is, based on USCS, the distinction in fine grains is determined based on its behavior. And we know in geotechnical engineering, this behavior of the soil is the most important factor for us. That's why USCS soil classification is preferred over AASHTO and MIT classification systems. Again, just it is important to highlight AASHTO soil classification is also a very popular one in construction of roads and this sort of things. But in geotechnical engineering, the most important classification is just USCS because it relies on the behavior of the soil in presence of water. So let's do some deeper study about the grain sizes. We know that 75 millimeter was the upper bound for gravel. At 4.75 we reached at sand, and eventually at 0.075 we reached at clay and silt. As you see, it is a little bit hard to work with these sizes whenever dealing with soils, because we are dealing with values which differ in order of magnitude. So, a very efficient in dealing with these sort of parameters is the logarithmic scale. You must be familiar with logarithmic scale. It expands the differences in order with the same distances so that we can have wider range for each range. Okay, so as you see now, we can easily distinguish the range for gravel, sand, silt, and clay. So we know that the coarse and fine grains are actually distinguished somewhere here, and there is another problem in dealing with soils, and that is due to the fact that whenever we try to study the grain size of the soils, we never deal with pure soils. I mean, it's quite rare to have pure sand, pure gravel, unless we are very close to beaches. Otherwise, we always have a mixture of all the components. So we need to, in order to report the grain sizes in a soil, we need to construct a diagram. The diagram developed is known as grain size distribution, where the vertical axis in this is percentage of finer. So let's assume we have a soil which is associated with this curve. At any point, it means that, for example, at 90%, which is associated with 2, it means that 90% of this, the grains of this soil are finer than 2 millimeters. For those who are less familiar with logarithmic scale, let me just explain how to read. So if we start from 1, right here, this will be 2, 3, and you go till reach at 10. Okay, after 10 the units will change to 10. So here is 10, here is 20, 30, 40, till you reach at 100. Okay, so this is how we read the values in logarithmic scale. So for example, let's inspect the value at 50%. This point represents that 50% of these soil grains are finer than, let's find this value, it's somewhere here, which will be 0.08. Okay, here it is 0.08. Okay, so this is how we read this diagram, and as I explained, this curve, which is quite a useful one, shows the grain size distribution in our soil. Whenever the soil is fairly good, developed and extended over different zones, I mean, for example, something like the one that you see here, it has some amount of gravel, some amount of sand, and also sand and clay. This sort of soil is called well graded, the one that we have here. Otherwise, if the soil is limited to a few groups, I mean either excess or deficiency of certain sizes, then it's called poorly graded. We will discuss it in later slides. So the significance of grain size distribution diagram is that it gives us the proportion of different grain sizes. It gives us a relatively reliable indication of the quality of the soil, and as I said, it shows us if the soil is well graded or not. Keep in mind, in USDS, we mostly by soil grain sizes, we refer and focus on coarse grains. Okay, so keep in mind it will be extremely informative for coarse grains. Okay, it is definitely less important with whenever dealing with fine grains. Okay, so now you know that by coarse grain we mean they are greater than the size 75 micrometer, and in these cases we used a series of sieves and just shake them to actually distinguish the sizes of the proportion of each size in our soil. Okay, this is how the test is done. So you put some amount of soil in the top sieve and just leave it in the shaker for something between half an hour to 1 hour, and the order of these sieves is that they eventually get finer and finer. So any amount of soil retained in each sieve means that it shows us the coarser values, or vice versa, the amount just passing shows the finer content. And most of the times, the last sieve that we use here is sieve 200, okay, which is actually representative of the upper bound for fine grades. Here you can see the opening sizes in US standards sieves. Again, note that in sieve 200, which is one of the most important ones, the opening sizes is 75 micrometer. Sieve number 4 is also the other important one, which the size is 4.75. This range will be sand, the upper range will be gravel, and below this, whatever we have will be the fine grain. In case you wish to actually find the proportion of fine grains, you can use the hydrometer test. Definitely hydrometer test is more complex test than simple sieving. And as I said, as soon as you propose complex engineering procedure, then engineers will not welcome it. Okay, that's why USCS has become the most common system. Let's have an example here about grain size distribution. Suppose we have 150 gram of soils and we are trying to do the sieving of it. These are the sieve sizes. These are the weights retained on each of these sieves. And we are asked to develop the grain size distribution for this soil. It is always important to note whenever we have whenever we are doing the sieve test, there is a pan just at the bottom. And as I said, some amount of soil is passing the sieve number 200, which is this one. So we should always be aware of that. We had 150 grams of soil. Just check how much soil we have here. The summation of these 5 numbers will be 141. So the remaining 9 grams will be in the pan, which are the amount of fine grains. Now we can easily calculate the percentage of retained soils. So over this sieve size, we have had 30 grams. So by dividing 30 grams by 150, we reach at 20%. We will do the same to complete every value here. The next step is to evaluate the accumulated values. For this, we should add up all the numbers till this row. For example, the values, accumulative values retained on sieve size 6.3 is only 20%. For the next sieve here, it will be the summation of these two. The summation of these two percentages, which is 42%, is retained on this sieve, okay? And we proceed till we reach at 94%, and the remaining 6% is left over here, okay? Remaining 6%. The important thing is that when we develop the grain size distribution, we always need to obtain the percentage of fine, not the percentage of retained. So we should subtract these values from 100% to reach at these values. This is the final values that we should use in order to develop the soil, the grain size distribution diagram. So I just saw one question which was about do we do the sieving with dry soils? The thing is, in grain size distribution, and the presence of water does not affect the results, because we are always dividing our values by the total volume, total mass of soil grains, okay? And the presence of water does not change anything. But you may have heard of some doing the test by applying some water so that they can do the sieving more rapidly. especially whenever they have clays, whenever the clay content is quite high and they do not wish to calculate or investigate the fine grains, okay? But in general, whenever we are speaking about grain size distribution curve, we rely on the solid grain. Now let's continue this example. So we should identify these points. So these are our points. Just for more practice, for example, this point, can you read this point? This point is something like 58%, this one, and the size is somewhere here, so this is 1, 2, somewhere between 2 and 3. It is, it is somewhere here, so 2.3 is some good estimate for this. Okay, at this step we just connect these values to reach at the grain size distribution curve. There are a few important values that we can extract from grain size distribution curve. One of the most famous values is the effective grain size, which is defined as D10. It means that you should just find the percentage of 10% finer and just read the particle size. Okay, it's somewhere here. This size is called effective grain size. This value is important to estimate the permeability of soils. That's why it's been quite an important value. So whenever we deal with soils, we could end up at different grain size curves. Whenever we have some uniform soil like this, all the grain sizes are more or less similar, then our curve is actually limited to one simple area. As you see, the sizes are very close, so the curve is actually within this range here. Whenever we have other sizes as well, small sizes and fine sizes, then the curve will actually be extended over all zones, something like this. This is called the well-graded. And now you can see an schematic representation of this as well. So whenever we have a well-graded soil, it has relatively all sizes and the voids are not that empty. So it will show better mechanical properties. Okay. And by poorly graded, let's see what has happened. We have removed a specific size here. As you see, the curve is now extended over one region, and it is gapped over some region and then completed. This sort of curve is known as poorly graded because of missing some amounts, okay? As I explained before. And whenever a curve is only within the zone of fines, as you see here is the lower bound for sand, so the majority of the soil is in fine range. Whenever the majority of the soil grains are in fine range, then the soil is known as fine soil. Okay, it doesn't matter any further that we have a good distribution of fine soils? No. As I explained before, the soil grain sizes are important whenever we are dealing with coarse soils. Okay, that's why this type of soil is referred to as fine. So again, the definition of well-graded and poorly graded: fairly graded, a fairly good representation over a rather of a wide range is known well-graded, and the excess or deficiency of certain sizes is known as poorly graded. Still, our definition is quite subjective, and it's not that useful by engineers. Anyone can say, no, this one is not that good, this one is not that bad, so it doesn't work. That's why we need to develop some more clear criterion to determine the grade of the soil. To do so, we define two coefficients: coefficient of uniformity and coefficient of curvature. Coefficient of uniformity, Cu, is defined as d60 over d10. Okay, so it shows how uniform is the soil. Coefficient of curvature, C sub C, is d30 squared over d10 times d60. So in addition to d10, we are referring to two more sizes, d10 and d60 and d30, which are also important. And whenever we calculate Cu and Cc, in order to determine if the soil is well graded or not, if Cc is in range of 1 to 3, then the soil is well graded. But it's not the only requirement. There's another requirement based on Cu. Cu should be either larger than 4 or 6. If the soil is mainly gravel, then there is some benefit. This type of soil is advantaged over the soils that are mainly sands. Okay, so whenever we are dealing with soils which are mainly gravel, if we have Cu of larger than 4 and Cc in range of 1 to 3, then it is well graded. If any of these two requirements are violated, then the soil is poorly graded. For sands, the requirement of Cu is changed to larger than 6. Now let's refer to the curve that we had earlier. Can you read the value for D60? So just find the point of the curve at 60%, and this is the point here. By reading the values, this is 1, this is 2, and somewhere very close to 3. So it is 3 millimeter. For D30, 0.1, 0.2, 0.3, very close to 0.4. For D10, exactly at 0.1. So based on these values, we can obtain Cu. Cu is C60 over D60 over D10, which is 3 millimeter over 0.1, which will be 30. Quite a big number. Now check coefficient of curvature, D30 squared over D10 times D60, 0.4 squared over 3 times 0.1, which reads 0.53. So, is the soil well graded or poorly graded? Because its Cu is way greater than 6, but C sub C is not within the range of 1 to 3. So the soil is not well graded. In fact, it is poorly graded. So the curve that we had in the beginning, that we thought it could be a well graded soil. In fact, it's not. Now let's talk about relative density. Relative density is a representative of how the soil is dense, and it's defined as Emax. It's represented by I should answer one comment. One of the students asked if the lecture today is going to last till 9. No, I think it will be ended at 8:40, 8:15, in half an hour from now, because we did not have the workshop today. So let's talk about relative density. Relative density is defined as the ratio of Emax minus E over Emax minus EMIN. But what is the meaning of Emax and EMIN? So whenever we are dealing with a specific type of soil, this soil could be in a very loose way. Whenever it's extremely loose, and there are some procedures and tests determined to evaluate Emax. Okay? On the contrary, there are other procedures that you should follow to determine EMIN, the minimum void ratio, the most dense condition of the soil that we have. These are here, and you can easily determine the current value of void ratio in order to evaluate the relative density. So you can see what are the important ranges for relative density. As you see, very dense is referred to relative densities of above 85, while very low is for 0 to 15%, and so forth. Next problem is that grain size distribution is not important or representative for fine-grained soils. So what is the solution for this? As we discussed at the beginning of this lecture, for fine-grained soils, the behavior in presence of water, or simply the plasticity, is the most important factor on its behavior. So by plasticity behavior, we mean that how far the soil has the ability to undergo unrecoverable deformation, okay? Like just a plastic without any cracking or crumbling. And we know that this behavior is mainly due to the presence of clays, and this will happen in the vicinity of water, okay? There are some procedures to determine how plasticity indexes of the soils are. The most famous contributions in this regard are based on Atterberg, which are renowned as Atterberg's limits. So Atterberg's limits are some criterion which actually classify the states of soil as solid, semi-solid, plastic, and liquid. So suppose we have a sample of soil and we want to discuss how variations of the volume of our soil sample versus its moisture content, W, okay? Let's assume we've got a sample of soil, we have added a huge amount of water to it. For example, we have 50 grams of water, we have 50 grams of soil grains, we have added 1 kilogram of water and mix it up. In this fashion, we have just a simple liquid. Okay? Eventually, by decreasing the moisture content, by, for example, evaporation of the water, eventually the soil will change from total liquid into a plastic matter. The transition from liquid to plastic occurs at liquid limit, which is shown by LL. And if we keep reducing the moisture content, the plastic behavior of the soil is converted to semi-solid. Again, this transition has another known as another limit of Atterberg, which is called plastic limit. But beyond one value, eventually the volume of our soil sample will not be reduced. Can you tell what is happening at this point and beyond this point? At this point, which is known as shrinkage limit, the soil will actually start to transit from fully saturated to unsaturated condition. I mean, instead of reducing the total volume, the volume has reached at some extent that it's not going to be reduced. Instead, water is actually evaporating and replaced by air. So in this range, we will move towards the unsaturated condition until we reach at fully dry condition. Okay. A very important index here is the plasticity index, which is actually the difference between liquid limit and plastic limit. It is one of the most representative values of the soil plasticity behavior. So again, note the last point that we have the soil at fully saturated condition is the shrinkage limit. Okay, and beyond that we will have unsaturated condition. So keep in mind that shrinkage limit used to be quite a popular parameter before 1920s, but eventually, because different experiments showed that it's not much reliable value and it's not that much representative, it was eventually it lost its significance. These are the tests that you need to do in order to determine the plastic limit of the soil. So you can refer to standards for plastic limit is determined based on the moisture content at which threads with 3 millimeters are cracked or crumbled. The liquid limit is determined by using Casagrande bowl. We just put our soil sample inside this ball and actually blow it. By blowing it, it will move 1 centimeter upward and it is released. In this test, we have a grooving tool, which we actually create a groove in our soil sample. This is the groove that we have created, okay? And eventually we keep blowing our soil sample again and again. And the moisture content at which half inch of this soil is closed is known as liquid limit. It is just hard to do the procedure in a way that 25 blows exactly close our groove for half an inch. Okay, so the definition was that the definition of liquid limit is also the groove must be closed by half an inch at 25 blows. Okay, and because it is practically impossible to reach at this value. We should do many tests to reach at this value. Instead, we can do it by using different curves. We just repeat the test for a few times. It could be 5 to 6 times, could be a reliable one. And we should draw this graph. As you see, the whole line is logarithmic scale. And by reading the value at 25 blows, it is one of the most reliable ways to determine the liquid limit. Alternatively, there are some ways that we can do the test by only one sampling. In this case, we should actually be relatively close to the liquid limit. I mean, the number of blows must be in range of 20 to 30, otherwise it's not that reliable. And we simply use this closed form solution. Just bear in mind that in this course, we will explain the test procedures, including this one and many more. I do not wish you to actually do any lab experiments, because in this course, we do not have any lab. We have it in our undergrad program, and I believe most of you have done this test. But my emphasis is that I do not expect you to know how the tests are done, how the procedure it is going on, but I want you to know what is our interpretation from these tests. Okay, for example, from Atterberg's limits, we are going to find out the liquid limits and plastic limits and so forth. Okay, so this is my expectation in this course. Now let's continue talking about fine soils and how we can classify them. There are very famous diagrams developed based on variations of plasticity index with respect to liquid limit. So in this diagram, a line is actually developed over the past years, which is known as A line. And this line is the border between the clay and silt. Whenever a soil, for example, let's assume we have a soil sample with liquid limit of, let's say, 50% and plasticity index of 50. So we are somewhere here, okay? Some point here, some point here. If we have a soil sample that is located here, it means below line A, then we will conclude that this soil is silt. On the contrary, let's assume we have a soil with liquid limit of 40 and plasticity index of 20, somewhere here, on the other side of line A. Then the soil is clay. So it is quite an easy job when we have the Atterberg's limit to determine what is the group of our soil. Okay, just go to this diagram and determine it this way. There is another important concept in this diagram, which is high and low plasticity. Whenever we are dealing with soils that have liquid limits above 50%, we name that soil high plasticity. While in cases that the liquid limit is lower than 50%, we call the soil low plastic. Okay, so from this diagram we obtain two important facts. First of all, whenever we find the location of our soil sample in this diagram, first of all we can tell if the soil is silt or clay, and secondly we can understand if it is highly plastic or low plasticity. So These are the different groups of soils that we can have. If we are above line A in high plasticity zone, we are CH. By CH, we mean clay with high plasticity. On the left-hand side of it, we have clay with low plasticity. And on the other side, as you see, in addition to M, we have O. O is organic soil. So, in addition to clays and silts, we have another class of soils which are organic soils, which are actually uh, made as a result of different type of plants or trees in long term. So again, the zone in this diagram is the same as silt. So as you see, if we are here on OH, then we have organic soil with high plasticity or silt with high plasticity or vice versa. And there is another important uh, zone here which is referred to as CLML. This zone is is actually referred to very limited number of soils where it has extremely low plasticity. So it really doesn't matter if it is clay or silt. That's why it's called both. Okay, so it's called CLML. Just just one question for all of you. How can you tell if a soil is organic or silt? This is a bonus question. I will give you by the end of our session today. If any of you can answer this first, will receive 2% bonus mark for this. Okay? Now let me see the question here. Can you explain how we can get any plasticity with 100% liquid? That was exactly my point when I told you we can have soils with moisture content of, let me do not go to the slide. We can have soils with the moisture contents as high as 500%. We have some clays that can have moisture content of 300%. Okay, so do not think we are always dealing with so normal soils that everything is quite normal. No, we may end up at some regions just near these zones as well. Okay, so let's go to our next slide, which is Casagrande's plasticity chart. So this chart that I just showed to you is not the complete version. This is the complete version. So as you see, this diagram, we have a line known as A line. The equation is here. Pi is equal to 0.73 times LL minus 20. Below this line, we are in silt or organic zone. Above this line, we are in clay zone. This limited region is the common region CL and ML. And there is another line here known as U line. U line, the equation is 0.9 LL minus 8. The importance of U line is the fact that in practice, we have no soil beyond line A. So if you happen to do some tests and end up at some point like here, I mean above U line, then definitely doubt about your test results. Okay, it cannot happen. It's extremely rare cases that we may end up at soils and just very close or slightly above this soil. But if you end up at somewhere here 20 and 40, it's totally impossible. Okay, so this U line is also another control for our test results. That's why it's also important. So soil classification systems will give us correlations which are beneficial to us about the understanding of the overall behavior of the soil. Meanwhile, there could be some special purpose systems as well that are developed for special applications. Always the procedures are quite clear that you may follow and end up at the classification, but here we will deeply explain USCS. You should follow the same, more or less same procedure in other systems. Okay, so in unified soil classification, always keep in mind soils typically have two letters. Okay, so each class of soil which have two letters, there's a primary letter and there's a secondary letter. The primary letter always is representative of the type of the soil. For example, the first letter could be S, which shows that the soil is sand. The second letter is a descriptive letter. For example, it is W. This means that we have a soil which is mainly sand while it is well graded. Okay, I'm looking your answers. I think none of you has still made it on. Be more creative. Ah, just did. Just one of you said it. Burn it. Let me see. Who said this? One of you said we should burn it. Okay. Good job, Joshua. Well done. You will receive the 2% bonus. Joshua Walenkic. You will receive the 2% bonus in this. That is exactly the case. So whenever you have an organic soil, whenever you are dealing with an organic soil, let me go back here. So as I said, we will have a common region for organic soils and silts, but in order to determine which soil are we dealing with, the best way is just to burn it. If you just put it in oven, eventually in time, because organic soils mainly have carbon, and carbon is burned in time. If you put the soil in oven for, usually it's left for 1 hour, and if it loses huge amount of its mass, then it has been organic soil. Okay, well done, Joshua. let's continue to the next slides. Okay, we were here. So in USCS, our objective is to actually attribute a two-letter name to each class of soil, where the first letter is the primary letter, the second letter is the descriptive letter. Okay? So whenever dealing with soils, the procedure suggested by USCS is as we are going to discuss right now. First of all, determine the percentage of fine grains. By fine grains, now you know that we should determine the amount of finer than sieve number 200 or 75 micrometers. So we will end by two different scenarios. One case is the amount of fine grains are more than 50%. In this case, the soil is referred as fine-grained. The remaining algorithm must go to step 2. On the contrary, if we have a soil which has less than 50% fines, then the soil is known as coarse-grained, and we should go to step 3 in the algorithm. So step 2 was whenever we have a soil with more than 50% fine grain, which is actually a fine grain soil. In these cases, we should purely rely on plasticity indexes of the soil, both the liquid limit and the plasticity limit. Okay, so the only step that we take is just find where our soil is located. Just read the liquid limit. For example, if you have a soil with liquid limit of 60% and let's say plasticity of 35%, somewhere like here, then the soil is TH, and that's it. Quite an easy job. So whenever we are dealing with soils with above 50% fines, the procedure is the most straightforward. In rare cases that you were in this zone, then the soil is CLML. So it has all, you should mention all of these names, okay? CLML is the name. And also keep in mind, most of the times with silts and with the soils below this line, most of the times we have silts. So in the remaining of this lecture or in many practical engineering cases, you'll just refer the name as HOML, not OHOOL. You should test it. You should put your soil sample in oven and test if it is losing a significant amount of volume of its mass or not. If it is not, then it is 100% silt. But most of the times from the beginning, you assume it's silt. Okay. Now let's go to step 3. So this is the case that we are dealing with a coarse soil which has more than 50% coarse grains. First of all, we need to determine the primary letter. So whenever we have a soil that has some amount of fine grains, then we can determine the fraction of coarses by in this way. FC is equal to 100% minus F. So this percentage is representative of the total fraction of coarse grains, okay? Based on this value, if more than 50% of FC is sand, then the primary letter for this soil will be S. And in case more than 50% of it is gravel, then the primary letter will be G. Now the second step, which is the suffix. So we have different scenarios here. The first scenario is the cases that we have less than 5% of fine grains. In these cases, we these sort of soils are known as pure ones. Okay, so we either have pure sand or pure gravel, and the important factor to this type of soil is if it is well graded or poorly graded. And you already know how to tell if a soil is well graded or poorly graded. Now you know how to pick gravel or sand, which is based on its dominancy in FC. And once decided, you should check these criterion here. If, for example, if the soil is gravel, you should check Cu larger than 4 and Cc in range of 1 to 3 and so forth. Okay. In this in these cases, you end up at two-letter soils like this one, SWGP. What is SW? Well-graded sand. What is GP? Poorly graded gravel. Okay. Another scenario that we may end up is the cases that we have over 12% of fine grains. In these cases, the suffix will be either M or C. In order to determine this, we should just go back to the Casagrande's diagram. Okay, so just refer to this diagram and determine where is the soil located. If the soil is located in silt zone, then use N. If it is located in C zone, just use C for the second letter. Okay, so in these cases we end up at SC, for example, or GM, clay sand, silty gravel. Okay, there is another range which is the transition range. Whenever we have fine grains in range of 5 to 12%, in these cases, you should follow a specific procedure. You should first assume the fine grains is less than 5%, and then pick a name about the grade as well graded or poorly graded. Okay? Next round, you should assume the fine grains are above 12%. In this case, you should pick a letter between C or F. Based on this, you will reach at two name soil. For example, SWSC, well-graded sand, clay sand. It will have both names, okay? So at the end of the day, we will reach at different classification for soils. For gravels, we can reach at GW, GP, GM, GC, and so forth. And for the borderline, we will reach at double name, like the ones that you see here. And for fines, you will reach at non-plastic or plastic ones like this. Okay, so I rapidly go through the procedure again. In USCS, in order to classify the soils, quickly pick the fine grains. So the starting point is the fine grains. Determine if you have over 50% of fine grains or not. And based on that, you will move to the next step. Whenever you are dealing with fine grain classifications, then you should actually use Atterberg limit. Just find where the soil is located, and that's it. The easy job. Whenever we are dealing with coarse grains, then we should first determine what is the percentage of coarse fraction, and based on the density of the sand or gravel in FC, we will determine if the first letter is S or G. The second step for coarse grain classification is based on the content of fine grains. If it is less than 5%, we actually overlook it, and it's a pure sample of soil. We decide if it is well graded or poorly graded based on coefficient of uniformity and coefficient of curvature. For fines above 12%, we determine based on how the fine content are behaving, and in the border range, in this transition, we should pick both names, okay? So the procedure is quite straightforward, and we will have a few examples to clarify it even further. So let's assume we've got a particle as a sample of soil with this data from the test, and it is mentioned that the soil cannot be rolled to a thread when it's moist. We are asked what is the soil classification. So this value is for sieve 200. So you can see 4% is finer than sieve number 200. So because we have only 4%, we have the room for up to 50% to determine to have the soil as coarse grained. Okay, so this soil is coarse grained. Next step is actually to see what is the distribution of coarse grains, if it is sand or if it is a gravel. So sieve at 4.75 millimeter, we are at 88%. So we are losing 12% as rocks and cobbles and this sort of stuff. We have started at 88%. Okay. So the lower bound is 4%. So the range is the difference of 88% and 4%, which is 84%. Okay. So we have from this 84%, the part which is dominant determines the first letter. So any part which has more than half of this 84% determines the first letter. Okay. So as you see, the amount passing sieve number 4.47 sorry, I said this value wrong. Sorry, my mistake. So this 4.75 millimeter is the upper bound for sand. This is lower bound for sand. Okay, so in this range we just have sand. Okay, so starting from 84% and reach at 4%, it will be 84%. This 84% is sand. Okay, Above this, we have 12%. This 12% is gravel, okay? So if you compare 12% against 84%, 84% is dominant. So the soil is mainly sand. For the suffix, we should decide based on how much fine we have. Firstly, because we have only 4% of fines, then we just overlook it, and we should only determine it based on whether the soil is well graded or poorly graded. To do so, we should use C, and Cu. We have the values of D10. D10 is 0.15, D30 is 0.425, D60 is 1.18. So Cu will be D60 over D10, which is 7.87, and Cu is D30 squared over D10 times D60, which is 1.02. Okay, then. So our soil is sand. Cu is above 6. Cc is in range of 1 to 3. We get that the soil is well graded. Okay, so the name of this soil in USCS will be SW. There is another example that I leave it out for the workshops. Noor will next week Noor will solve a few examples. Next week Noor will start the lectures, and we'll start with solving a few examples from phase relationships, and then continue to solve the remaining example from soil classification. Let me check if you have had any questions here. I can see some of you have had difficulties with the final example. So let's go through that example once more before we finish this session. So we were dealing with a soil where this grain distribution were reported based on sieving tests. So as you see, 0.075 is sieve number 200, and for 0.75 is both the upper and lower limits for sand. So all this range is representative of sand, and it is said that it cannot be rolled to a thread when it is moist. This shows even the negligible amount of fines that we have here is most probably a silt instead of clay, because it doesn't show any plasticity. Okay. Our next step was actually determining what are the ranges in our sieves. So we are dealing with 96% of fines, because only 4% is smaller than sieve number 200. So the remaining 96% is more, because this is the range for sand. Then the difference between 84 and 4, which is for 84%, is the sand. The remaining 12% at the top of here will be gravel. So because the sand is dominant, then the first letter will be sand, and the second letter will be determined based on the grade of the soil grains, given we had D10, D30, and D60, even though you may not exactly have the exact values, sometimes you will need to extract it from the diagram. Okay, so I mean, you have to draw the diagram, and in case you did not have D30, you should try to interpolate it. Okay, by the way, here you have D30, D10, and D60. So once you calculate CU and CC, then you can decide if it is well graded or not. So let me get back to your comments or questions. Any more comments for today or any questions? Is there a reason we describe soil USCS and not Australian standards? USCS used. The thing is, the USCS is one of the most famous classifications worldwide, and we really want you to be familiar with this soil classification. And we do not have the time to go through other classifications. Even AASHTO is also quite an important one for you in practice, but we leave both of these important classifications to your own study. Do we have divided PowerPoint? The handout is too large. Yeah, I can share you a smaller size for handouts as well. I will share it for you on the Moodle. You can use that one as well. So I think it was the last comment for today. So thank you so much, everyone, for being patient and quite active in the class. So next week we will again start at 5, as I said again. Please make sure you attend the workshop. It will be the first 1.5 hours. For that, try to be interactive with Noor and try to bring all of your questions to that time. It could help others to learn more as well. Okay, so it is quite an important part of our course to have these workshops. Just after that, I will continue the lectures. As I said before, we will have some direct consultations with myself on Fridays from 10 to 1. You're more than welcome to come over to the campus. I think the school is now open with restricted access and restricted number of students with social distancing. So if you wish to come over, you can send me an email and we can do the arrangements. Otherwise, you can actually contact me via online consultation like everyone. So I can see one last comment here. Can we create a document and type the detailed solution? We'll transfer it. One of the students is asking if you can type the solutions and have it in a document and keep it in a good document and make it PDF and share the PDF to me. It's totally fine. It's actually quite good job if you make a good document for all of your courses, and later on you can refer to these to have to have them for your future references. At the same time, it's totally fine to have it handwritten. It's totally up to you. It's totally up to you, so it doesn't make any difference to me but you. Okay, so thank you everyone for today. and try your best to study the topics and challenges and be well prepared for our next session. And see you next week. Bye.